Okay, hello everyone. This is Mrs. Lim. This is part 2 of chapter 9, thermal processes. In this part, we'll be zooming into convection, radiation, as well as the applications of how conduction, convection, radiation is being used in our daily lives. Okay, so moving on, convection. Convection is the process of energy transferred by means of convection currents due to difference in density. So the difference between conduction and convection is that for conduction, the particles do not take the energy and move. They just pass the energy by vibration of particles. But for convection, it is the particles that takes the energy and move. Okay, the particles that is being heated up will move further apart, and therefore the volume increase, density decrease, and therefore it will move upwards. Okay, and then the one that is being colder or cooler will be denser and it will sink. So it's by the movement of particles that transfer the heat energy, and this movement of particles is known as convection current. Okay, so let's zoom into the diagram. Next. Okay, so over here you can see this is how convection happens. Over here, there is a fire, so the heat passes through the metal pot by conduction, and then the water at the bottom will gain energy by conduction again because it's touching the hot metal pot at the bottom. So the water at the bottom will get heated up first. Okay, and when the water gets heated up, the particles expand, not the particles expand, the water expands. Okay, just take note that particles do not expand. It's the water that expands. The particles move further apart, and therefore the water expands. And when it expands, it becomes less dense, it will rise. Okay, and then when it rises up, it loses some of the energy to its surrounding, and it becomes denser now. Okay, because it's not so hot anymore. Okay, particles comes closer together. So when it becomes denser, it sinks. And this will set up what we call a convection current. Okay, this cycle up and down, it's called convection current. So another one that you can see just now is the heat source at the center. Now I have a heat source at the side. The same, the liquid at the bottom is heated up. Again, the keywords are already underlined and bold for you. The liquid will expand. Take note, it's the liquid that expands, not the particles that expand. The liquid expands, becomes less dense, and rise. Okay, and then so when it reaches the top, it cools down. So the cooler liquid at the top is denser and sink. This will set up what we call a convection current. This movement due to the density difference is a convection current. So over here, heat is being transferred by the net movement of the particles. The particles takes the heat and move up. And then when it cools down, it sinks down again to take more heat again from the heat source. So this is how convection occurs. I need to see the word less dense, denser, and then it rise or sinks, etc. Okay, and set up a convection current. These are the keywords. Okay, I'll not play this video. You can play it yourself at home. We move on directly. I want to talk about convection current. Some of the questions will ask you to draw convection current. Just take note that for convection current, there are two types. Okay, there can be a single loop or a single cycle, we call it, and a double cycle. So whenever is the heat source is at the center, it will be a double loop. Okay, so for example, I'm going to draw on the diagram how is convection current being formed in each of the following cases. So the first one, the heat source is exactly in the center. So every time whenever there's a heat source, it's always going up directly at the heat source. Okay, there is no other ways. Okay, then where is it going down? You need to think of where in the whole part will the air be, or the air or the liquid be the coolest. Okay, the coolest should be the furthest away from the fire. So it'll be here. Okay, so let me do it properly first. Okay, so this side will be the colder part. So this side will be sinking, and this side will be sinking. Okay, so I just continue to form my loop and get this. Okay, you can join them up, you can don't join them up, it's up to you. Okay, so this is when the heat source is exactly at the center. But what happens if the heat source is at the side? Then again, then it will not be a double loop. Okay, over here is a double loop. But over here, if the heat source is at one side, then it will be a single loop. So the heat source is over here, so this side will go up, and then the other side will go down. Okay, so the cycle will be like this. It's a single loop cycle. Okay, next we have a radiator. A radiator gives out heat energy. So this part will be hot. So this side, the air will go up, and the other end, extreme end, will be cold. So it will sink down. And again, I will form a single cycle because the radiator is at the side of the room. Next one, for an ice cream. Ice cream doesn't give you hot air. Okay, the surrounding air that is near the ice cream will be cold. So the surrounding air will sink. Okay, sink on both sides. The ice cream, it will sink down. And then the warmer air from the other places will then rise and go towards the ice cream to be cooled down. And then again, it will be cooled down by the ice cream, and then it will sink again. So this is the convection current around an ice cream. Okay, so I will not play this video. You can even watch this video yourself. It's like I'm going to introduce some smoke over here. Then I have a candle. You will see that the cycle. Okay, so this side is cooler air will sink in, and then it will come to this candle, which will then causes the warm air to rise. So you can see through the smoke particles. Again, because I couldn't see air particles, so I'm going to introduce smoke as I can see the smoke particles. Okay, so summary of so far what we have learned. Conduction is a process of energy transfer whereby energy is transferred by vibration of particles from one particle to the next particle. Metal is the best thermal conductor because metal consists of free electrons. They can move very fast through the metal and before they collide with the other less energetic neighboring particles and transfer the energy very fast. Convection, on the other hand, is the process of energy transferred by means of convection current. Because of difference in density, the particles will take the heat or take the energy and move along with it. Okay, the hot one will always become less dense and rise, and the cooler one is always denser and sink. Okay, so this is the difference between conduction and convection. So for conduction, energy is transferred from particles to particles. In convection, energy is transferred by the movement of the heated particles. Then next, we move on into radiation. You need to take note that for both conduction and convection, you need a medium, you need particles, you need solid, liquid, gas to be present in order for energy transfer to take place. Okay, because for conduction, you need the energy to be passed from particles to particles. For convection, you need the energy, the particles to take the energy and move. Okay, but there are certain scenarios whereby you do not need any medium, you do not need any solid liquid gas in order for energy to be transferred. One very good example is how energy from the sun reaches us on the earth. Okay, we know that there is a vacuum in the outer space. You can see this diagram, sun to the earth, in between is outer space, which is a vacuum. There's no solid, no liquid, no air in the outer space. Okay, but the energy from the sun can still reach the earth. Okay, the sun is very hot. It will still be able to reach the earth by a process called radiation. Okay, so what exactly is radiation? Radiation is the process of energy transferred by means of electromagnetic wave. And specific, I'm going to write here, is by what we call the infrared radiation. Okay, we'll learn about infrared radiation more in depth when we are on the topic of EM waves. Okay, but of now, you just need to know that radiation is the process of energy transferred by electromagnetic wave called infrared radiation. Okay, there is no medium required. All objects, okay, which has a temperature as long as it's above 0 Kelvin, which is -273, which is majority of the items are all above 0 Kelvin, or I could say all of the items are above 0 Kelvin, they would be absorbing and emitting infrared radiation all the time. Okay, so radiation or infrared radiation depends on the rate of absorption or emission depends on three factors: the surface temperature, surface area, surface color, and texture. Okay, so for surface temperature, you can see that as I cool something down, the temperature doesn't drop constantly. It's not a straight line down. Okay, it's a slope, it's a curve. Okay, so at the start, the curve is very steep. It means that the temperature drops very fast. Within a short period of time, the temperature drops a lot. Okay, this is because at the start, my temperature of my object is higher. Okay, the temperature between the object and the surrounding is greater. So the greater the temperature difference, the faster the rate of emission of thermal energy. So at the start, a lot of radiation is taking place. A lot of radiation of infrared radiation is taking place. Temperature drops very fast. Okay, however, as the temperature drops, the surface temperature drops. Okay, the temperature difference between the object and the surrounding decreases. Okay, so the rate of energy transferred to the surrounding will also be lower. Okay, but then, oh, another case is you can see over here, I have object H, which is initially of a higher surface temperature than object C. Object C has a lower surface temperature. So as object H has a higher surface temperature, it has a larger difference between the surface temperature and the surrounding. So you will see that for object H, the decrease in temperature or the steepness of the slope will be greater than C, okay, which has a lower temperature. So the higher the temperature of an object, the higher the rate of emission of infrared radiation. Okay, next factor is the surface area. Okay, so if I have a small pot and a big pot, obviously the big pot will lose thermal energy faster. Okay, so you can see over here, if I have a small area, only this area is going to emit out infrared radiation. But if I have a bigger area, then all the areas will be able to emit out a greater amount of infrared radiation. So a larger surface area will emit, it will also absorb more infrared radiation. Okay, or it will absorb faster as well. Next is the color and texture. Okay, the surface color and texture does affect the rate of radiation. It affects how much radiation gets absorbed or how much radiation gets emitted. Okay, so we move on to the next slide. These are the things that you need to know. Black and dull surface, okay, are very good absorbers, but they are also very good emitters of infrared radiation. On the other hand, silvery white surface are very good reflectors, but they are very poor absorbers as well as poor emitters of infrared radiation. Okay, so just take note that if I am a good absorber, I can take in heat, a lot of heat, absorb a lot of heat very fast. I am also a good emitter. It also means that I can emit the energy out very fast and very efficiently. Okay, so good absorbers and good emitters all belongs to the same category. But in your exam, when you're writing answers, you can only choose one. You cannot choose two. So you cannot write something like, oh, black is a good absorber and is a good emitter. You can only choose one because they are totally opposite meaning. Absorb means you take in, emit means I'm giving out. Okay, so we always look at what is the main purpose of the object. If the main purpose of the object is like a solar panel, is to absorb energy, we say that it's a good absorber. Black is a good absorber. But if the main purpose is to cool something down, for example, like a cooling fin, okay, main purpose is for cooling, it's going to emit energy out. So I would say that black is a good emitter of infrared radiation. Okay, I'm not going to say, oh, black is a good absorber, so it can absorb out a lot of heat from the object, and then it's a good emitter so that it can emit out a lot of heat to the surrounding. No, just choose the main function of that object. Okay, just take note also, because you are going to learn about radiation, in Sec 4. So nowadays, we do not accept like, oh, it's a good absorber of radiation, it's a good emitter of radiation. You need to use the word infrared radiation. So it's a good absorber of infrared radiation, it's a good emitter of infrared radiation. Okay, radiation itself is not acceptable for now. Okay, some of the applications, we have a vacuum flask over here. A vacuum flask is the main purpose is to help to keep things hot or cold. It minimizes the energy transfer between the liquid inside and the surrounding. So if my liquid is hot, I will try to keep my liquid inside hot. And if my liquid is cold, I will also try to keep my liquid cold. I want to minimize heat transfer. Okay, so these are the main parts of a vacuum flask, and all these parts plays an important role in minimizing the heat transfer. Okay, so I'm going to go through the parts first. There's a plastic stopper at the top, okay, which traps air. Okay, if you open it, then the air is no longer trapped. The air will be able to move up, out of the flask. Okay, there is a double wall glass container. Okay, so this one is a glass container inside, and it's double layer. Okay, and there is a layer of vacuum in between the walls. Okay, the vacuum is over here. So between this outer layer and inner layer of the glass is a layer of vacuum. How to get a vacuum? They will just have a special machine to suck out all the air so that there's no air inside it. There's no particles. It's a vacuum. Okay, and then the inner walls of this glass are also coated with a layer of silver. So they have what we call a silvered surface on the inner sides of the glass, double wall glass. Okay, and then how does it help to minimize heat transfer? Okay, so it helps to minimize all three processes: conduction, convection, radiation, as well as evaporation. Okay, you will learn in the next chapter that evaporation does cause cooling. Okay, so what happens over here? The first one, I have a plastic stopper at the top. Plastic is a poor conductor. Every time I talk about material, I think of conduction. So plastic is poor thermal conductor. So it reduces conduction. It doesn't prevent. Eventually, there will still be some heat conducted, but it slows down the entire process. So it reduces conduction. And because of this plastic stopper at the top, the air cannot escape. So hot air cannot rise out, cold air cannot come in to cold air cannot sink in to cool down the surrounding liquid. So we say that it reduces convection. Okay, whenever air is trapped, you can say that it reduces convection. Next one, there is a vacuum between the two double glass wall. So we know that for a vacuum means that there's no particles, means it prevents, okay, prevents, not minimize, conduction and convection confirm cannot take place because of the vacuum. Okay, next one, but I still have radiation, so I need to minimize this radiation. So how do I minimize it? I use a silvered coating on the inner side of the double glass wall. Okay, so silver is very good because silver is a good reflector. Just take note that every time they ask about silver, white, okay, the answer is always about is whether it's a poor absorber or poor emitter, except for vacuum flask. Vacuum flask is most of the time is only with the use of vacuum flask or in questions where we talk about the inner surface. Okay, inner surface, outer surface. Okay, whenever there's inner surface that is silver, most of the time is a good reflector. So it helps to reflect the infrared radiation either into the flask or away from the flask, depending on where is the hot item. Okay, this is the second part. I will stop now.